I can determine when a relation is a function. That should sound pretty familiar because that's what we did last time as well. But this time we're going to be looking at non-numeric relationships. I guess some will be numeric, but just remember that everything still applies. If you don't have repeating x's, then you don't have to worry about it. So if your x's do not repeat, you'd say, okay, I know it's a function automatic. If they do repeat, then you got to go to that second question and ask if their corresponding y values are repeating. Because if they are repeating, then it's a function, but if they are not, then it is not a function, okay? So one of the ways we're going to see these relationships, and we just saw that example, is it's going to say something like, is blank a function of some other blank, like this, okay? If we see something like that, just know that it sets up, it's asking is y a function of x, which is kind of reversed, so sometimes we get this mixed up. So be careful, it's always is y a function of x. I guess I should have put a question mark there. So this just is to help you make tables to see what your x and y values are, so you can distinguish the difference, okay? But this is also why last time when we looked at function notation, it's f of x. Because remember, f is kind of the y. The function is based on x. So it's a function, y is a function of x. And that's why it sets up like this, f of x. And right here, what we're really concerned about here is the mappings. So functions can also be described by non-numeric relations. A mapping is a representation of a function that helps to better understand non-numeric relations. And we'll go over each of these. But remember, for a mapping, right, so it's got kind of two boxes or blocks like this. In order for it to be a mapping, like whatever values are over here, doesn't really matter what values there are. In order for it to be a function, there can only be one arrow coming out of each of the values over here, all right? And it doesn't matter where they point. Like it can cross like this. It doesn't matter if they cross. All that matters is how many arrows are coming out of the values, okay? Because the left box is the x's and the one on the right is the y's, okay? Now, if by chance there were like two arrows coming out of one of them, such as this one, then you say, oh, just from these two arrows right here would say that this would then not be a function. So that's all we're looking for in mappings. Everything else works the same though. For graphs, we're going to run the vertical line test. And for tables, we're just looking for x values that repeat and then looking at their corresponding y values. So here's a relationship between input. That's whenever we see input, that's always our x values. And the output, of course, is y values. So that means that the x's, just like usual, should be the left box on the map. And then the y's should be on the right. And it is, just like it shows. So we just need to determine if this is a function. So, well, just like we said in that last slide, I don't see any arrows, multiple arrows coming out of any of these values in the circumference. And so this is the circumference of a finger, and then it determines the ring size. So we would say in this case that it is a function. Each x value has only one arrow out of it. It may not be good English, but I hope it works. So that tells us if it's a function or not. Just visually looking at the mapping, we should be able to tell that. Now it wants us to write the ordered pair, so now we need to look at the arrows and determine what is pointing at what. So to start out here, we got 14.1 millimeters, and this arrow is pointing to 3, which gives us an ordered pair of 14.1, comma 3. So that's an ordered pair that we could put on a graph right there. And then the next one here, 14.9 millimeters and size 4 ring. Or this next one, 15.7 millimeter finger circumference, and you'd have a size 5 ring. And then finally this last one, a 16.5 millimeter circumference finger would be a size 6 ring. And that's all the ordered pairs. And just from the ordered pairs, we can see that the x values do not repeat, which means right away we could say just from that information that it is a function also. Then decide if the relationship is a function, and this one we'll explain. So input, remember input is your x's, and the output is the y's, right? So it says the input is the state a person lives in, and then the output is the team they root for in college football, I guess. Okay, is it a function or not? Now again, without having to, we don't really need to look at the values inside the boxes. They could be numbers, they could be labels like this. It doesn't matter, but the first thing I notice here is that there's 2 arrows coming out of Utah, right? Not that that first one would be a big one, but since there are 2 arrows coming out of Utah right there, this one is not a function. Not a function. There we go. Well, 4, it wants the ordered pairs. Again, now, okay, we can do that. So just from the purple there from Utah, and we got Utah. I'll type these ones in as well. That's our first ordered pair. The second one is Utah. Then that second arrow points to Utes. And then the third one is Nevada. That's the X value. And then the Y value, Utes again. And then that fourth one, ordered pair, Arizona. And that arrow points to Sun Devils. There we go. So that is all 4 ordered pairs from this one. Now, I know it didn't ask for this, but I'm going to go over it just kind of as a quick review. If by chance this asked for the domain and range, the domain, yeah, we do need fancy brackets, would be Utah, Nevada, and Arizona. And this is nice the way the mapping works for the domain and range, because even though values repeat in the mapping, just like with domain and range, it does not show it more than once, other than with the arrows, right? So that would be the domain, and then the range would be all those Y values. And then Utes, and then Sun Devils. So the input is the city a student lives in, and then the output is the high school they go to. Is it a function? Well, if we look at this one, we see from Salt Lake City we got 3 different high schools coming out of there. 3 arrows there, and then from Provo we got 2. Now, doesn't matter which one you say would make it not a function, it still is not a function. But again, that's because we don't know, and if we think about this, hopefully it makes sense. We couldn't say for sure which high school someone goes to if they live in Salt Lake City. You may say, well, it depends on where they live. Yeah, we don't know where they live. We just know it's just Salt Lake City. That's all we know. So we wouldn't be able to say for sure which school they go to. Or Provo for that matter, right? If someone said, hey, I live in Provo, you'd say, well, we don't know which high school you go to. But if you lived in Camas, you'd say, okay, we know you go to South Summit High School. So if it was just Camas in here, it'd be like, okay, that's a function. But where we got double and triple arrows coming out of some of the input here, not a function. Now this one's interesting because sometimes it throws students off just a little bit, okay? But if we consider this situation and just think about what makes a mapping a function, because this is a mapping, we should know right away that this one is a function. a function. And why is it a function? It's because each of the inputs, the ages, has only one output. Or it only has one arrow coming out of it, right? Bam. Now, just so you know, math people would say this in a little bit more nerdy of a way. They'd say each of the inputs or x values has only one output or y value that corresponds with it. You don't have to say it that way, though. So as we've seen, there are many ways to represent a relation or function. In the following problems, you'll be given one representation of a relation, and asked to create additional representations, then you'll be asked to determine whether the relation represents a function or not. Fair enough. So here's our story. A candle is 27 centimeters high and burns 3 centimeters per hour. An equation that models this relation is C equals 27 minus 3h, where C is the height of the candle in centimeters and h is the number of hours that candle has been burning. And if you wanted to, you could say that the time is the x and the height is the y's. And how do we know that? Because generally for us, the x's are always going to be the left column and the y's are always going to be the right column. So keep that in mind. And it's also true in the table or the mappings like they've shown right there. Now they didn't tell us any specific values to look for, so we're going to make up our own. And I would just start with 0, like, okay, how tall is this thing at 0 hours? And whether you use the equation or not, I am going to use just the words right here. It says a candle is 27 centimeters high. So that's how tall it is in the beginning or when it started. So I'd say, oh, how tall is it in centimeters? Boom, 27 centimeters tall right there. Now for me, I would just say, I would just be going up by hours. Some of you may choose to do decimals or fractions, which I think is more work than we need. But what I know from each hour is that it's burning 3 centimeters every hour, right? Now burning would indicate that it's taking 3 centimeters off of the height. So where 0 hours gave us 27 centimeters, another hour would burn off 3 centimeters. So 27 minus 3, 24 centimeters for 1 hour. And if I burn this candle for another hour, it would burn another 3 centimeters, which would make that 21 centimeters tall. And if I burn it for another hour, so now 3 hours, it's going to burn off another 3 centimeters. 21 minus 3, 18. And then another hour would be 4 hours, so it's going to burn off another 3 centimeters, which would then make that 15 centimeters tall. Now you could continue this table if you wanted to, but that's about as big as it is. So that's as much as I'm going to make it, okay? But I do need to make the mapping here. And so I'm going to list all of my x values. Or you could just list these as ordered pairs one at a time, right? It's at 0 hours, we know the height was 27 centimeters. Boom, there's an arrow from 0 to 27, right? Which comes from this ordered pair here. Or for 124, we'd say for 1 hours, it was 24 centimeters tall. And so I have an arrow from 1 to 24. Or for 2 hours, 21 centimeters tall, same thing. 2 hours will point to 21 here. And then 3 hours, 18 centimeters tall, so 3 hours, 18 centimeters. And finally, just with the values that we have, 4 hours was 15 centimeters tall, so 4, arrow to 15, boom, there we go. And yes, it is possible some students are like, I want to mix these up so that the arrows are pointing lots of different directions. Whatever, okay? But you still only have one arrow coming out of each of these. So we would know pretty quick, just from the table and the mapping, that this is a function, right? From the table, we would say there's no x values that show that they repeat, so we wouldn't even have to check the y values in this case. We'd say automatically we know that it is a function. So that also means since it is a function, and we know c is the y and x is the h, we could write it in function notation. I know it didn't ask for this either, but I'm still going to do it. So I'd say it's y is c, so I'd say that's not y anymore, it's f of x. Remember that function stuff? And then this would equal 27 minus 3, but instead of h, we'll we'll use the x there again. Right, and remember, this x in the parentheses is the x in the equation. So if we wanted to find f of some value, you just replace x with whatever value's in this parentheses here. So that's a nice little review from last time also. All right, but it does want other representations of this as well. In fact, let me move this over just a little bit. So let's list these out as ordered pairs. I know we kind of did that in the table, but we'll still list these up here. So we got 0, 27, the first one, and then there's 124 is the second one, and then 221, and then 318, and then 4 hours, it was 15 centimeters tall. So there's our ordered pairs, but we still need to make the graph on this, and they did not label the axes or scale them for us, so we're going to need to do that on our own. So I'd say the labels, which are given in the table and the mapping, right? I see the x's here, that's hours, so I'd say x, that's hours, and then the y, that's the height. So they're labeled the axes. Now we just need to scale the axes. So I'd say, okay, yeah, there's 0 hours, and then I'm just going to go by 1 hour for each of the lines. So at the end there, that's 10. And then the height. So this one, I'm going to be a little bit more methodical about this one, okay? So I know that the candlestick is burning at 3 centimeters per hour. Okay, I should kind of, if I can, anyways, I should make this part of the scaling of the y-axis, because the height of the candle is based on centimeters, so I know it's burning at 3 centimeters per hour. So that means if I can make these lines go by 3s, then it should work out very well, especially since it's starting at a multiple of 3, which is 27, right? At 0 hours, it's 27. Now, the other thing I would want to know when I make this graph is I want this point to be on the graph, because we know from writing equations from graphs that seeing that y-intercept it's pretty crucial, okay? So I need to get at least up to 27, and I can do that pretty quick if I make each of these lines represent a 3. So 3, 6, 9, 12, 15, 18, 21, 24, 27. And yeah, you could stop there if you wanted to, but 30, 33, 36, I'll stop there, okay? So each of the lines on the y-axis is representing 3 centimeters. And we're going to see that this is going to turn out very nice once we start putting this on the graph, right? Because the first ordered pair, 0, 27, boom, there it is, right? 0, 27, 0 hours, 27 centimeters tall. And then 1 hour, it would be 24 centimeters tall, so that's this point. So see how that next point, it falls on one of the grid corners? That makes this extraordinarily convenient, and if we continue this, each of the other points should land on grid corners because we know it's burning 3 centimeters per hour, and each of these lines is going down by 3 centimeters each time. So the next point, 2 hours, 21 centimeters tall, 3 hours, 18 centimeters, 4 hours, 15 centimeters. So yeah, we got all these ordered pairs on the corners. Now the other thing that we should know is that if we wanted to continue this pattern, we could. And it's going to tell us one other piece of important information. And that is how many hours it will take for this candle to burn out. Well, it's going to burn out once it's 0 centimeters tall, right? That's this point right here. And right there, since this is 10, this has to be 9 hours. So it's going to take 9 hours. If it's burning at 3 centimeters per hour and it started at 27 centimeters, it's going to take 9 hours to burn out. Now, the next thing we should consider is, do we connect these points? Well, in order for us to connect the points on the graph, we have to be able to have half of both of the labels. So you can have half an hour, and you can have half a centimeter. So that means that we can connect these points, right? Remember, like the gumball ones, we wouldn't connect those because the pennies, you couldn't put in a half penny on that. Now, the other thing you'll notice about this line that I made is I did not put arrows at the ends. If I put an arrow here, it means that we would be going into the negative hours, which we shouldn't be able to do, which would also indicate that this candle was getting taller the farther back in time you go, which is true on the graph, but it doesn't make sense if it started at 27 centimeters. It would just be flat after that. Same after it's burned out, it wouldn't continue to go into the negative height or some kind of second dimension or something like that. It would just be flat after that as well. So we don't need to put arrows on this line. So is this a function? Well, we already determined if it was with the table and the mapping. And again, the mapping is, or the table kind of tells us with the points. So yes, this one is a function. But also, the line that we made on the graph is going to pass that vertical line test, right? If I take this line, this red line here, and I scan this, it's never going to go through that red line, the vertical line, more than once. So it is a function. All right, here's another situation. I'll kind of go through this one fairly quickly though. So I got my x value, right? And the first one shows negative 1, 0. So in the table it shows negative 1, 0, which is, by the way, an ordered pair. And then the next one, the arrow there is 0, but it's pointing to 1. The next arrow is from 0 to negative 1. So that next arrow would be from 1 to 2, and then the next one from 1 to negative 2. And then the last two would be from 2 to 3, and then also 2 to negative 3, right? So that would be the table, but the table also gives us the ordered pairs, like this. Each of these is just an ordered pair. I mean, they come from the mapping, so the mapping gives us ordered pairs as well. So we can put these on a map. Negative 1, 0 would be this point. 0, 1 is this point. 0, negative 1 is this point. 1, 2 is this point. 1, negative 2 here. 2, 3 is here, and 2, negative 3 is here. And even without using the vertical line test, we should know that this is not a function, but we can still show the scanning, right? Right at the edge here, it shows that it goes through once, but as soon as you hit any of these other values, it's going through twice. So this one is not a function. And again, that's because it does not pass the vertical line test. Now, if you said, well, there's 2 arrows coming out of the mapping for some of the x values, that would work as well. All right, let's look at this one. Function or no? That's correct. It is not a function, because if I run the vertical line test, since it's a graph, I should. So I'm going to take this vertical line, I'm going to scan it, boom, there it is. This, just on the first time it goes through some points, 1, 2, 3, 4 times, 4 points go through this vertical line at the same time. So this one is not a function. And again, that's because it does not pass the vertical line test. Yeah, if we think about this, right, it was saying, is the child's height the function of a child's age? And yeah, we should kind of know that, yeah, if we look at a child's age, we wouldn't know exactly how tall a child would be just based on the age. Now we just got ordered pairs. And looking at these ordered pairs, is this a function? That's correct. It is not. Yeah, and we can see the first thing we'd want to see is, are there any x values that repeat? Now, since this one does have x values repeat, we need to go to that second question and look at their corresponding y values. And right here I have 2. Right here I have 4, right? Since those are not the same, the y values for those corresponding x values, then this one is not a function. So this one's kind of like our bell work. We've got a curved line. And remember, curvature of lines does not determine if it's a function. What does is the vertical line test. So will this one pass the vertical line test? No, it will not. Therefore, this one is not a function. Yeah, we got this vertical line here in orange. And just scanning it, just right at the edge here, you can see it goes through twice. So yeah, not a function. Well, what about equations? Equations work just a little bit different, and there's a couple ways to look at this specific equation, depending on how you remember it from the last unit. So the first way I would look at this probably is with the table, okay? So I got x and y values, and we only need a few values, but we can only put x values in this table that make this equation true statement, right? And the only value I can think of is 2. So if I said x is 2 right here, the y value can be whatever you want it to be. It can be 0. If x is 2, you could say the y value is 1. If x is 2, you could even use, I don't know, fractions if you wanted to, like 3/4. Or you could use even negative decimals. It's not going to matter. Something like this. But the x value just has to be 2 every time, right? And just from this table, we should see that we have x values that repeat, but we have different corresponding y values. So just from the table, we should be able to say this is not a function. Now, the other way we should know from this x equals 2 business is the graph. Okay, so the graph, we got the x-axis and y-axis. Remember, x equals 2 is a vertical line where x on the x-axis is 2 right there. Now, that's kind of a crappy vertical line, but I did my best. And if we show a vertical line test on this one, see if I can get this to work, and then we could see, if I had drawn that better, that this purple line is going through this green line in an infinite number of points. So yeah, this one's still, from the graph, not a function. So equations like this, at least the equations that we've done so far, if we can change equations into slope-intercept form, it's automatically a function, all right? And this one we know just from experience, this one can be changed into slope-intercept form, right? You'd say, I'm going to subtract the 3x from both sides here. It's going to zero that out. Then I would drop the 6y, which equals, we got 18 and a negative 3x, but we don't want to combine those because they're not like terms. So it's going to be negative 3x and positive 18. Now divide all the terms by the coefficient of y, which is 6. And yeah, now we have slope-intercept form. So the slope, negative 3 divided by 6 is going to simplify into negative 1/2. And then the y-intercept, 18 divided by 6, is positive 3. So that would be a y-intercept at 0, 3, with a slope of negative 1/2, which also indicates that from the slope we'd go, or for the slope, we would go down 1, and then to the right 2. From 0, 3. So on the graph it would look like this. X-axis and y-axis. And would have a y-intercept at 3, right here. And we'd go down 1 to the right 2, down 1 to the right 2, something like this, which would give us a line like this one. And we can see this line will easily pass the vertical line test. If we run it, it would only touch this line at once at any given time, right? There's a vertical line. And then we scan it, only touching once, boom, it's good. So it is a function. All right, just looking at this mapping, function or no? Nope, not a function. That is correct because we got 2 arrows coming out of the B letter grade, all right? So this is a good example to point this out, right? If I said your grade is a B, could you tell me your exact percent? No, you could not, which makes this not a function. Well, let's reverse that situation, right? Let's say that the letter grade is a function of percentage. So remember, is y a function of x? So in our table now, or mapping even, we would say this is our percentage, and this is our grade. It's a G. Now, if I said, hey, your percentage is an 88%, would you know your exact grade? Yeah. Sure. Right, you'd have a B+. If I said that you had 95%, would you know your exact grade? Sure. What if I said you had a 93% though? Yeah, you'd know your grade's an A. Now, does it matter that those 2 lines are pointing to an A? No, it does not. What would matter is if suddenly, right, we put a C here and it was like 93% you could get an A, but you could also get a C. Right, that would seem really jacked up, which is why it doesn't work, right? And so, we're going to get rid of that garbage. And so, yes, this one just by thinking about it, hopefully, we would know that this one is a function now. So by reversing those, you'll change it from a function to not a function, or from not a function to a function. All right, here's the table. It shows us the time of day and then temperatures that are given. So based on the time of day, would we know the exact temperature? Yeah, for any, specific day, yeah. Right, and even where it shows 8 a.m. and 7 p.m. we had the same temperature, okay, that's not a problem. What would be a problem is if suddenly 8 a.m. was pointing to like two different temperatures like that, right? It's not, so that's good, which makes this one a function. Now let's reverse that though. Is time of day a function of temperature? And remember, it's always is y a function of x, like this. So in the table, we'd say, all right, x and y, right? Just like it showed on that last slide. Like, yeah, 65 degrees, that would be the temperature here. So on that last slide, it showed, what was it, like 8 a.m. and then 65 degrees. It could also produce, 7 p.m. So right, just from that, and we should be able to know this without having to see that last example, but if we have a temperature, it could be several different times during the day, especially in Utah where we are. Weather here is pretty jacked up, but that alone would be enough to say, yeah, this one now, not a function. So is this one a function? Just a table. Well, in order to determine this is a function, we just look at these x values, which should always be this left column here. And I do not see any x values that repeat, which automatically makes this one a function. All right, here we have input, which is the x values, and y value, output's the y values, right? Now, whether you make a table or graph, I think the mapping actually would help us out on this one, especially with the hint, okay? So if I had a mapping like this, I need this one to be a little bit bigger. And then this one, so x, right, that's the city. And the y one, that's the state, one on the right. So right here, just based on what they told us about Independence. Okay, Independence, that's some city somewhere. Like this. Well, if there's 16 states that have a city named Independence, how many arrows are going to come out of the city? Maybe 16. 1, 2, 3, 2, whatever. I'll try that again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I ran out of space. But you get the idea, right? There's a ton of arrows coming out of Independence. Well, not a ton, but 16 of them, if I draw them all. And that would make this automatically, very quickly, just from the mapping, not a function. No, there's our objective. I can determine when a relation is a function. And again, whether it's non-numeric, whether it's in a mapping, whether it's in a table or a graph, or just straight ordered pairs, we should be able to make that determination. And yeah, we also saw some function notation and domain and range stuff again, so I think that's good stuff.